good afternoon. We were discussing how to improve the performance of the cycle in the previous class, and we discussed about the superheat in order to improve the reduce the reversibility. In the previous class we have seen, I think this is not working here. Then we mentioned in the previous class that we can go for superheat like this, but the problem is the metallurgical parameters are the important ones here. So, therefore, there can be some maximum temperature of the cycle is important. So, here if you look at the specific heat of the water is greater than that, and mainly the materials used is important in this case, which we discussed last time. And again another thing is, if you go for higher temperatures, if you go for 400 to 500, there is a reduction in strength by 30%. Okay, in the previous class we have seen, and the maximum steam temperature can go up to 620 degrees Celsius so far. Then we also discussed how the pressure plays an important role. Pressure of the heat addition, mainly heat addition pressure is important here. So, we can keep the maximum temperature is the same, the cycle maximum temperature, highest temperature of the cycle same, but if you increase the pressure we get additional work output, but there is a penalty here which we lose some part of the work. And there are one advantage is, if you increase the pressure, obviously you will have a high additional work, but there is a reduction in work on the other side. Not only reduction in work, but also this important after the expansion of the steam in the turbine, the exhaust condition of the steam becomes wet, more wet. So, therefore, there is a possibility of eroding the blades. As we go higher pressures like that, and if you increase the temperature by keeping the temperature, cycle temperature same, then as you go for higher pressures and pressure, and if you go for single expansion, single turbine, what happens is it is not good, because it goes towards the whatever incremental heat energy or work we get out of that, but there is a loss also from the other side, from here to here. So, therefore, when you higher pressure is always better, but not with a single expansion. But if you go beyond this dome, that is what we discussed in the previous class, that this is a supercritical condition. It goes to the supercritical, and exactly it goes out of the saturation line, that is a dome. And when you go for supercritical conditions, you have to go for you cannot keep the same temperature, and if you go for single, then you have to also increase the temperature. So, the temperature here, then if this 0.2 is most important, why? Because it should not go below 88% of the dryness fraction. So, therefore, then if you increase the pressure and expand from the exit of the boiler or your steam generator, obviously you have to go for higher temperatures also. If you do not want to go for higher temperature, there is other method, reheat, we will discuss that. So, this is the supercritical case. As I also mentioned that this part is heat addition here, and this heat addition is in a single component, it is called once through boiler or supercritical. Last time I explained this, and the pressures are in this range, the supercritical pressure greater than 22.09 megapascal or 220 bar. So, if you draw a line vertically from here, suppose what you have to do is, this is a constant pressure line, it goes like this, then how do you expand, means you fix this point here, this point to about 88%, and then vertically go up, and wherever it meets, that is a corresponding temperature. But if you go for single stage expansion, this is only one turbine is expanded here, but I think in supercritical this is not advisable, going for single, because your temperature is also fairly high, and having high pressures and high temperatures in the boiler is not possible. Not possible means it becomes very prohibitively expensive, and is because we look at the power generation mainly with respect to economics. So, it may not become economically viable. So, I have shown how a supercritical power plant operates, but in practical case it is not the case. We will see what is the practical case. Then another important thing is reducing the pressure from this also I mentioned last time, reduce the pressure of the heat rejection. What we discussed in the previous one, increase the temperature pressure where you are adding heat. Okay. See for heat engine you have two. So, you can this temperature pressure here you can increase this, but why do not we this T2 and P2 you can also manipulate this such a way that we will have a higher efficiencies. Here the main important thing is the temperature is the most important thing at heat rejection. You cannot go below atmospheric temperature. So, then you can adjust only the pressure according to the atmospheric condition. Okay, this part you can go further here like this. Okay, then you can get this work and then go to the pressures like this, high pressures by pumping. Then you get additional area, but the what is the problem here is, as we go down, okay, you cannot go down because the temperature is the limiting parameter, because atmospheric temperature, and the pressure corresponding to that is the saturation pressure. Okay, you have to go for the saturation pressure corresponding to that temperature. Okay, so generally it is the negative suction pressure here. You cannot go like this. There are two reasons. One is the atmospheric temperature. Even if you wish to go down, then another important is this, you have seen from 2 to 2 prime to 2, what is happening, the condition of the steam, exhaust condition. As you go further, you know the drainage fraction is defined by this ratio here, this ratio by this ratio by this ratio. Okay. So, now as you go down, this is moving towards mixture side, that means you have a high wetness. So, therefore, this is also not advisable. So, therefore, the only parameter which limits here is this atmospheric temperature and corresponding pressure. This is also good idea, but we cannot go below, and especially temperatures in India, atmospheric temperatures are very high. So, therefore, corresponding pressure may be 0.1 bar you can go and suction and do that. This is another one. I have already explained earlier, whatever is written in the text here, it is already explained. So, this thermal efficiency of the condensing steam power plants will be less in the warm regions, which I have mentioned, as compared to the. So, that means the power plant efficiency differs from location to location, that means what is the atmospheric condition, and also if in Chennai there is a power plant, it gives different performance in the night as compared to the day, because your night time temperatures are different. Okay. So, therefore, this is the heat rejection also plays an important role. That just now I mentioned excessive water content in at the exhaust. Here, if you go here, you have excessive water content. Here, this at point 2, this location, you have excessive water content which may erode the blades, maintenance will be high. So, then we have seen 3 or 4 parameters. Superheat we have seen, but means increasing the temperature of the highest temperature of the heat addition, we increasing the pressure, supercritical pressure, and reducing the pressure at the condenser. So, these, but then if you see except superheat, all the other two, increasing pressure, you have some penalty the other side, but only except increasing temperature, but the temperature you cannot increase because it is a metallurgical this. So, then under these limitations, how to improve the performance and how to come up with an optimal condition, then how can the performance of a power plant cycle can be improved. This can be done by increasing without increasing the temperature of the turbine, because this is a temperature is an important highest. See, we will keep always the most important parameter is the highest temperature of the cycle, that we will keep that, and then with respect to that how do we improve the performance of the system, and with the maximum permissible temperature. So, another important is this liquid content at the exhaust of the turbine is also important. So, we cannot go, there is a maximum permissible temperature, we cannot go below this, because our limiting parameters is here and here. So, you operate within that dome. How do you come up with the best way? Because you have a highest temperature as well as lowest temperature limitations. That is what your efficiency, 1 minus T2 by T1, T1. So, these two, we within those given conditions, how do we make a best power plant or most efficient power plant in this. So, then the performance improvement can be done by two important aspects, that is reheat and regeneration. Reheat and regeneration. So, what is reheat, what is regeneration, I will discuss. We will discuss with the first pressure. So, if you increase this initial one was like this here, I think it is not working. Initial one is no board is also there. So, initial we thought will increase the pressure, but what happens, this is a disadvantage. Then why do not we combine, for the initial cycle was this 1, 2, 3, 4, but if you increase the pressure there is a increase in energy work output, but there is a decrease here. So, therefore, this why do not we compare these two combine them, if you going for a higher temperature as well as this one. So, if you combine and come up with a new cycle which combines this. So, that is important here. How do we do that? Keeping that, this is the one which you can come up. Okay. Okay, we can ask this. Anyhow, my photograph is not important. We can use the board, but here anyhow I will make use of this itself. So, now if you combine this, your new cycle will be like this. It is see here now 1, 2, 3, 4, 5, 6 and 1. Okay. This is the cycle. What we are doing is the first initially in the boiler the heat is added between 6 and 1 here. Okay. It is similar to the previous one, and from there this is the highest temperature of the cycle, and then you expand to some level in a turbine, and after that you take the steam and put it back into the boiler. Boiler means which consists of the entire system. So, then you bring it and then you add some more heat to raise its temperature to the highest again back. See, this is expanded here and there is some work done, and after that take it and further expand, further add heat and to the same temperature as the maximum temperature, and from there you expand till the condenser. This is a condenser pressure. So, that this is above 88%. If you expand from here, what happens is it becomes wet at the exhaust. So, now what you are doing is you are taking it back and doing it. So, you always represent first, in order to do that, first when you want to solve the problems, you need two things important. One is a schematic and TS diagram. How do you do schematic? In the beginning I have shown you can put like this. This is the boiler which consists of 3 components I have mentioned earlier. So, from here, 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 and it goes into the turbine. Then it comes here and it rejects heat and then comes back by a pump. This is a heat rejection, this is a condenser, and here heat is added, and if you take this as 1, this is 2, this is 3 and this 4, and I have mentioned B and 1 prime in the previous case. So, 4 to B is the economizer, and B to B 1 prime B to 1 prime is the evaporator, 1 prime to 1 is superheater. In the this is the standard cycle, but now what we are doing is this part. So, after this you expand in a turbine here. After expansion here you bring it back and heat it and take it, maybe you can add another turbine here and add to this. Okay. Then further expand and take it is the same again, after this condenser, then you have pump, then it goes back, comes back. Okay. So, this is the furnace, you are bringing back the working fluid and heating further, and so this is 1, this is 2, 1, 2, 3, 4, 5 and 6. Okay. This is a schematic, and if you represent 1 is here, I think. So, the boiler portion is same here, I think in the my previous case this I used as a B and this is 1 prime, okay, this evaporator part. Then it goes to 1, then expanded here. So, if you you can connect the shafts or you can put it shafts separately also. So, here this is WT1, this is WT2, because there are 2 turbines, and when this part after expansion in the first turbine, then it goes to some pressure here, this is a pressure line. Okay. This pressure is actually, at this pressure you are further heating. So, since this turbine, first turbine is operated at higher pressure, then this is called HP turbine, high pressure turbine, and this is LP, low pressure turbine, because this is operated at low pressure as compared to this one. So, now once you plot this TS diagram, it is easy to find out what you are essentially to find out is what is the efficiency of this. Okay. What is efficiency? W net by Q 1. Okay. What is Q 1 here? What is W net here? W net is equal to, what is the power developed? H, this WP WT1 plus WT2, the work done here as well as work done here, minus of pump work. See, the pump is here, no pump work. So, therefore, WP, only one pump, by Q1, heat is added. Where heat is added? Heat is added here. So, heat added from 6 to 1, 6 to 1, no. So, that means here Q 6 to 1, but anyhow we represent everything in terms of enthalpies later. So, is that the only one heat added or any other additional heat added? Plus Q 2 to 3, this here also heat added, correct? So, therefore, this is the heat addition. Now, how do you find out all these? Simple, enthalpies, find out enthalpies at different locations from steam table and substitute. But since why? Because you can write specific enthalpies. Suppose here what is WT1? WT1 H1 minus H2. Is it this is for 1 kg, it is a specific enthalpy, okay, specific enthalpy. Then WT2 is H3 minus H4, okay. This is what? WP H5. H6 minus sorry, H6 minus H5, no, this 5 correct only. What is it not correct? Because let me see here. H6, this is a pump work, no? This is a pump work here. Pump work is H5 minus H6 minus H5. The pump work. But here when you I have included minus here, no, in the okay, here in this efficiency equation I put minus Wt plus Wt1 plus Wt2 minus Wp. Okay, in that net it is coming. So I think now I erase, this is clumsy, I will erase all this. I hope you have seen that schematic. Again I will redraw that. For better understanding, you can see here. Generally I put heating as a register, okay, but sometimes they like this boiler as one box, you can see here, and the condenser is written in this. Different notations are there. You can also use as a register to transfer the heat from one to the other as a heat exchanger. So this is what you can see here. One is high pressure and low pressure, and the part where the heating is done before expansion in second turbine is called reheater. So this part is called reheater, okay. This part is called reheater, okay, because we are reheating the same steam. I think I have mentioned this. This is a ideal cycle which I have already, I need not have to repeat that again, you can put it here. Cycle efficiency is given by this. I think this is minus here, but not plus, okay. So now what is the net, whether this net output will increase or decrease? Reheat is good or bad? Why it is good? Because see, we are getting some additional output, okay, but we are also adding some additional input also. This part we are adding, no, additional heat, but you are getting some additional. So when you do this, it should be positive, then only it is worth, otherwise it is not worth. You understand? The work output which you get for the input which you give, the additional work output which you get for the additional input should be more than or positive side, then only you can go for reheat. Otherwise, if you are heating more like this, but whatever the additional output you are getting is less than that, then it is no use, okay. So therefore the net output of the plant increases with the reheat, so it will increase. And apart from one advantage is, another advantage is we can operate, see, if you would have been single one, it would have come here, but since we are increasing here, so some turbine quality of turbine exhaust is also improving. Improving means you can make it close to 88%, that is the improvement. So advantage with this is you can go for higher pressures by going for reheat. If you go for higher pressures, what happens as you go higher pressure, if you expand in a single one, it becomes wet. Instead you go for reheat and expand further. So therefore you can one advantage is of operating at higher pressure and also getting some additional output. So this is the one which I have already mentioned here. Then actually the main objective of improving the performance is improving the mean temperature of heat addition. Always in this case we have to add increase the mean temperature of heat addition. In the previous case we have found no, the delta H minus delta S is called mean addition of mean temperature of heat addition. So, here you look at that this mean temperature of heat addition is improved because of see the average area under this curve is improving with the given temperature. So, therefore, the mean temperature of heat addition increases, and it increasing the superheat by using higher pressure also. Just now I mentioned same thing, high temperature steam. What is the meaning of the advantage of heat addition is you can also operate at higher pressures, that is an advantage of that. Then use the reheat, and this Tm, this mean temperature of heat addition is also increased by reducing the amount of heat added at low temperature. This means, see, the heat added between 6 and 1 is at high pressures. This is the higher pressure boiler, and this reheater once you expand, the pressure is reducing. Okay. Then this heat addition is at low pressure. In reheater the pressure is low, so there we are adding heat here, that is the meaning of that. So, therefore, by doing this, what happens is you instead of only transferring heat in the 3 components, you are also transferring heat, additional heat in another component. So, that because we have a highest temperature of the flame 1800 degrees Celsius, and that by adding reheat, what happens is you are extracting more amount of energy from the flue gases. So, otherwise it would have gone waste to the atmosphere. Okay, generally you know that 2/3 is rejected into the atmosphere. So, in the furnace another thing is this irreversibility could be eliminated, but the another problem here is you see that if you look at the one stage single subcritical single phase diagram, which I had shown you earlier. This is the one we have defined pinch points in the previous classes. What is the pinch point? The minimum temperature difference between the 2 streams is called pinch point. One pinch point is here and another pinch point is here, because this is the flue gas, this is a flue gas side, and this is the working fluid, it goes working fluid in the opposite direction, counter flow heat exchangers. And in a network of heat exchangers, wherever you have a minimum temperature difference between the 2 streams is called pinch point. And if you have a maximum difference, then it is it's not good, because it involves high irreversibility. In this figure, where do you have a high irreversibility? One point is here, because here you have a huge temperature difference, another point is here. How do you reduce this this irreversibility? By going for reheat. This irreversibility can be reduced by going for reheat, because you have seen here this is the fluid. So, this is the fluid. So, here heat is transferred here as well as here. So, therefore, you are reducing irreversibility there by adding reheat. But this there is a big reheat, big irreversibility here, large amount of irreversibility between this and this, okay, this and this. This irreversibility is a major thing. So, this irreversibility we should minimize. How? That is called regeneration. Regeneration is this, if you eliminate, you cannot completely eliminate, you can reduce that. That is by process called regeneration. So, what is the meaning of regeneration? What is the meaning of regeneration is you take internally the heat and add regeneration. So, after regeneration means this you have expanded here, is not it, till here. Then what you do is you take this part, generally take this part, for example, I will plot a schematic. This is a simple without reheat, you say sorry, this is a boiler and it goes to the turbine here, and after expansion you take these. During expansion, during from here to here expansion, what happens is its enthalpy drops and also its specific volume increases. That is why you have expander. Okay. What you do is you take these and turn around the turbine and then bring it and pump it here. It is called regeneration. That means while expansion, while the steam is being expanded in turbine, you bring some part of the heat and add to the outgoing or incoming working fluid, that is called regeneration. So, maybe I think I will because this is a bit clumsy, I will show you in the next one. The ideal regeneration means here it is reversible. You know, in turbine expansion is isentropic. Isentropic means there is no heat transfer, okay. It is a reversible. So, then you can wind a heat exchanger within the turbine mechanically. Of course, see it is like this, you can take heat and take heat some part of the turbine heat during the expansion and bring it back. So, the one which I showed you earlier, that you know wind or wrap the steam pipes around the turbine after expansion, and so that the heat during the expansion where some heat is transferred to this, and then the inlet fluid which is going into the boiler will have at a higher temperature, so that you will have less reversibility. But ideal process of expansion is a isentropic. Isentropic means there should not be any heat transfer, but when you introduce some heat exchanger and wrap it, it is not a see your dome is like this. So, here see this is isentropic expansion, but when you remove heat, this cannot be isentropic, it will cool, it will lose some heat to the this one. Then obviously, we are going to lose some heat. Have you studied Stirling engine? Stirling engine is a regenerative engine. Okay. During the expansion, some heat is transferred, so that it will be, then what happens is instead of heating, you will have a better heat transfer the other side. I will show you this, but it is not practical ideal regeneration. Ideal regeneration means during expansion you remove heat, but that is not possible because we cannot have a heat exchanger within the turbine like this. Okay. And second thing is it may not be ideal expansion because it deviates from the this one. So, therefore, I have mentioned. Another point is when you remove heat from the turbine, what happens is this exhaust gas steam will become more wet. So, then again for this last stage turbine blades will get eroded. So, therefore, this is ideal regeneration is not possible. Therefore, we have to go for a different way of regeneration. We use heat, and but it is a different regeneration. This is called regenerative feed water heating. So, before entering into the boiler, see here the water is pumped here to this is a boiler part, okay. And before entering this here, you bring this heat and raise the temperature here, so that this irreversibility is reduced from here to here. Okay. What you do is take some part of the heat and this one. Instead of doing in the turbine, you take some part after expansion and mix it and do that. That is called regenerative feed water heating. I will show you how it works. So, this is the normal cycle, which my standard cycle 1, 2, 3, 4, B 1 prime 1. This is a standard cycle. So, what you do is this is a single stage turbine, of course, single expansion. After expanding to some level, then you take it this way. You see, after 1 to 2 it is expanded, and then some part of the mass is taken, and after you taking this mass, if you take 1 kg of mass is entering into the turbine, and after a certain level of expansion you take m1 mass, and 1 minus m1 is further expanded here, and then the heat is rejected in the condenser and pumped to the next level pressure, this pressure, and combine 1 plus m with 1 minus m with 1 m1, then what it becomes 1 and then it goes. Okay. So, have you understood that some part is taken, because as after expansion in the turbine, some part of mass or some mass of the steam is taken at low pressure, and it is added with this one, so that this heat is combined with this. What is the advantage and disadvantage with this? See, suppose if it would have been 1 kg mass complete expansion, you will get what is the work here, work done by the turbine here, work done by the turbine is equal to H1 minus H2 plus from here to here, and from here to here also expanded, no, H2 minus H3, correct? It is not correct, because this is 1 kg of mass, this is 1 minus m kg. So, 1 kg is expanded from 1 to 2, then the next stage is 1 minus m1. Okay. So, if it would have been a single stage expansion, this work is more than the earlier one or less than? It is less as compared to single expansion with 1 mass. So, that means we are losing some work out. Okay. That is that. That means it is not good. But so what happens is the heat addition. Where is the heat added? Heat addition is here, Q1 is equal H1 minus H7. The heat is added here between that. But in the previous case, heat is added from 4 to 1. So, this heat addition is not there now, because of taking some heat from the turbine. So, therefore, when you plot the flue gases diagram, here A2 I think F or something, which in the previous class. So, initially the irreversibility is from here to here, but now irreversibility is from here to here. Okay. So, therefore, we are reducing the irreversibility. The temperature difference between two streams is reduced. So, therefore, you have a less irreversibility, that is the advantage here. Okay. So, the Q1 is also reduced because you are adding at higher temperatures. So, this is reduced and work is also reduced. If both are same, the rate at which the work reduction is equivalent to the rate at which you heat addition, then there is no effect, is not? There is no effect. Going for regeneration is useless. But an additional thing here is one advantage with this is you are reducing irreversibility. Second thing is, if you look at Q1 and Q2, what is Q1 and Q2? Q1 is heat addition, Q2 is heat rejection. Where is the what is the ratio of this? What is the approximate value of this? If this is 1, how much it would be? Typically, what is the value of that? What is the efficiency of this turbine? Efficiency of the cycle about 30%. What is the WT is how much? It is only 30%. Okay. Remaining 2/3 is rejected in the condenser. So, the meaning of that is, so Q2 is equal to 2/3 of Q1. 66 almost 60% is rejected into that. So, that means you have a massive condenser condenser, so much heat rejection means 500 megawatts means you should have a massive condenser. For going by if you go for regeneration, what is the Q2? Q2 is where? Here. Q2 means from 1 minus m, Q2 is equal to 1 minus m1 into H3 minus H4, correct. So, in the previous case here it is a 1. So, we are reducing the mass of the exhaust steam which is rejected into the atmosphere. So, that means the condenser size much lower than the previous one. So, the cost of condenser will come down. Is it clear? So, therefore, the heat rejection, you are reducing the reversibility, you are also going for reduction in the condenser side. So, this is the advantage of going for, I hope you understood that. So, now, so the heat rejection will be less in this case. See here, now another important thing is the economizer size, because this part is economizer from here to here. If you go here, now here economizer size is only this much. We are not only reducing the condenser size, but also economizer size. Clear? Economizer size has to be here, no, from economizer is heat raising the heat from here to here, but whereas here from now economizer will be here to here. So, that is a advantage. So, now you have seen here, no, in this case, so based on this you can say that this is called regeneration. Regeneration means taking steam after expansion some level and take some steam and mix with the feed water heat, okay, mix with the feed water heat, that is called regeneration. So, now here how many times we have taken? Once, single time. You can take more times also. You can, why you are taking here? You can take here and add here, and you take here and add here. You can have infinite steps, okay, take them. Then if you take infinite steps, what happens is it will become like that, the curve, okay, if you take continuous. But then what happens is your cost and other issues will come. So, therefore, you have to go for not one time, maybe finite times, some in generally in a most modern power plant it may vary from 7 to 9 feed water heaters. So, you understand, 7 to 9, we will discuss how that is. So, this is called feed water heating, which is it is a heat exchanger. Now, I will show you how you represent in terms of schematic. There are 3 types of see this, if you look at here, this part where the heat is the heat from this is added to the water which is coming from the pump. So, therefore, these are mixed and further pumped here. So, therefore, how do we do that? How do we what is the source of irreversibility? Sources of irreversibility. Now, we reduce irreversibility by reducing this, but what is the source of irreversibility? We have mentioned combustion is one, heat transfer, mainly heat transfer is one, and then friction, fluid and solid friction. The other one is the throttling, okay, and another one is mixing. If you bring 2 streams and mix it, then it is irreversible. Actually, here at this point we are bringing one stream of at this pressure at m1 mass, and another we are taking from this pressure here, this pressure line is this from this pressure and this here, and pumping further. So, that means you are mixing 2 streams. When you mix 2 streams, there is a possibility of irreversibility here. some irreversibility is created. But then how do we do that? How do we avoid this irreversibility? Then we have to go for configuration of feed water heaters. There are different types of feed water heaters, mainly 3 types. One is open or direct contact type, direct contact. The other one is a closed with drain cascaded backward, and the other one is pumped forward. The drains pumped forward. Okay. I will explain you how this work. See, open or direct contact means you bring one high pressure steam, low pressure steam, mix it. Okay. That is a simple open mixing, is simple, but what happens is the irreversibility problem. And what you do is bring high pressure, high temperature steam and heat to the other one, but there is no contact between them. It is like heat exchanger. This is a contact heat exchanger, there is a non-contact heat exchanger. The other one is how to, then after transferring heat, whether you go forward or backward, which is that we have to see. Then this we will discuss quickly one after the other. Regenerative cycle or regeneration cycle with the open feed water heater, the one which I showed you here just now. What happens is that pressure P, pressure 2, see here, this is a boiler pressure at 1, the pressure is at highest pressure, then this is a P1, this is a P2 and this is P3, which is a condenser pressure. Okay. So, from you are expanding high pressure to low pressure and further low pressure. So, then you one stream is taken m with mass m at 2 and added here with the another 1 minus m stream at from lower pressure. So, what is that? This is at one pressure and this is another pressure, no. So, what you can do is, where are we adding these 2 streams? This point, no, this point, okay. See, adding, taking stream at high pressure, mixing into the low pressure, there is no problem, okay. Why? Because we are high pressure to low. But if I want to add low pressure steam at a higher pressure, what I have to do? See, because this is coming here, another one is here, bringing this to here, there is no need, it come automatically because it is a pressure, lower pressure. But I want to mix here, take this and put it here. What is the meaning of that? I have to pump it, I have to pressurize it to that level, okay. You got my, so therefore one pump is here. I will show you the schematic how it will be. So now if you look at the schematic here, after expansion in the turbine, again I am using different symbols different times, because first I used resistances, and this is why, because to have a, you should have exposure for different symbols, that is why I am showing. I do not want to have a consistent symbol, so that when you refer different books, different symbols are there, but again whenever I am showing that, I will mention that what is that exactly. So, this turbine after expansion to 2, it is M1 is taken here, and this 1 minus m is further expanded here, and then go to the condenser and heat is rejected here, and from this condenser pressure is lower than this pressure. So, we are mixing here, mixing a middle point where this is taken here and then this is condenser. So, you need to pump it to this pressure. So, therefore, you need a pump, and after mixing this, then you have to go to the boiler pressure. This is a boiler pressure, therefore, you have to again further pump it after combining 2 streams. This is another pump, clear. And this pump is operates between the pressure 2 to pressure 1, okay. The stream is pumped to the next pressure. As just now mentioned that the condenser can handle only 1 minus m1 mass, so therefore heat rejection is less, and the mixing is happening here, both the streams. So, it is operated at high pressure. If you want to operate at low pressure, what will happen? Can you operate at low pressure? Can you mix it? You can, why is, sir, you are having a mixture, what I will do is I will bring it back and put it in the condenser and from there again pump it. There is no use, is not it? So that you can have one pump, no need to have two pumps here, correct. So then what happens, again there is no change in your condenser size, there is no change in, because when you are bringing it back to the, and another thing is when you want to bring high pressure stream to low pressure, what happens? You have to expand it. There is no turbine here. If you expand freely, what is there? A throttling. Okay. Again, it is a irreversibility. It is uncontrolled expansion. You take some stream at high pressure and reduce abruptly, what happens? It is uncontrolled expansion. Okay. So therefore, it is not a good idea without, otherwise the entire power work goes off. So therefore, better you keep it that and try to pump some amount. Where are you pumping? You are bringing it back to the saturation condition here and pumping. So this is I have already explained. Now this is anything, see the pressures, no, I have explained this. 1 kg of steam is extracted at P2. See the steam which is extracted here, what is the meaning of this is, this turbine is bleeding. Bleeding means taking some steam. Okay. This is called bleeding, taking some steam at some pressure is called bleeding, and the steam which is bleeded is called bled steam. Okay. This is a correct word, bleeding. So here how many bleedings? Only one bleeding. If you take one more here, this 2 bleedings, 3 bleedings, like that. So the steam which you bleeded is called bled steam. Now again I am writing energy balance here. I have explained you the energy balance just now, but again turbine work is from here to here 1 kg, from here to here is 1 minus m into this enthalpy, and heat rejection is 1 minus m into, I have already shown that. The pump work is same here. Sorry, pump work I have to mention here. See this is 1 and the condenser is smaller. Pump work is the 1 minus m is pumped to from here to here, from 4 to 5, that 1 minus m H5 minus H4 plus another pump is there here. This pump handles 1 kg, because this M1 comes from the turbine and 1 minus m comes here, then it is pumped further pressure. So this is 1 into H7 minus H6. Heat addition will be from here to here, H7 minus H1 minus H7 1 kg, then heat rejection, rejection is this here, 1 minus M1 into H3 minus H4. Then the mean temperature of heat addition, I have already defined this for regeneration cycle. Here initially if you look at H1 minus H1 minus H7 by S1 minus S7, this is the mean temperature of heat addition for regenerative cycle, whereas without regeneration this will be from here to here. So heat addition will be like that. So that is H1 minus H5 by S1 minus. So this is the S5 minus S. Instead we are going for this. Okay. So the ratio of this to this will be higher than this. So mean temperature of heat addition is improved by going for regeneration. So therefore this is greater than Tm1R is greater than Tm1. So that is why we go for regeneration. And what type of regeneration here is, it is a mixing. Mixing means open. This is there is a mixture where the heat is transferred from high pressure high temperature steam to low pressure low temperature steam, and then this is pumped to the next boiler. So this becomes a feed to the boiler. So that is why it is called feed water heater. So it is a open type feed water heater. Then next one is the closed feed water heater. Closed type feed water heater, and this is called drained cascaded backward. Drained cascaded backward. the meaning here now, see in the previous case sir, 2 pumps are there, why we need 2 pumps, we will eliminate 1 pump. How can we do without again going for this. So, this is the one you can see, again different symbols I am using here for boiler here. In this case I use boiler like this, but here you see this boiler another, because there are 2 circles means it is a boiler drum. Okay. Boiler, this is mainly used for subcritical conditions. Okay. So, then it is expanded in a turbine from 1 to 2, and some part is taken here as a bled stream, and then further is expanded here 1 minus m, then it is expanded, condenser rejects heat, and this expanded after condensation you pump to the boiler with a single pump. We are bringing back to the condenser just now what I mentioned, and putting everything in the condenser and pumping with a single pump, and there is no direct contact of these. There is no direct contact with this stream. This is one stream and this is another stream. The heat exchanger is opposite direct counter flow. So, this is a heat exchanger where this is called closed feed water heater, there is no direct contact of the fluid. So, therefore, no mixing, therefore, no irreversibility. Then it goes, and single pump is used which can handle the entire mass, then you are bringing it here. Generally in condenser what happens is we have to reject the heat, but this is steam. Okay. Here it is a liquid after condensation. So, therefore, we cannot afford to allow the steam going into the condenser. So, therefore, this is introduced trap. The trap is that allows the only liquid to pass, it does not allow the vapor to pass through, that is what trap is. Now, I have given you symbols here 1, 2, 3 here 1, 2, 1, 2, 3, 4, 5, 6 this one, and the other one is 2 to 7, 8 and 1. Can you plot TS diagram for this? I will give you some time. I will take one point here. So, it is expanded like this, but in between you are taking, see always better to take at the saturation condition, because you cannot de-superheat. See, you know that no, this if you look at this, I will explain you. After pump, this is a constant pressure line. Okay. Constant pressure means from here to here, what is the state of the fluid? It is in compressed liquid condition, it is a liquid. The liquid is sensibly heated to the saturation point here, saturated liquid, completely liquid here. Then from here to here 2 phase, and this is completely vapor, and this is superheating. So, sensible heating, evaporation and superheating. If you go from the back, that means you can also come in the reverse direction. Okay. This from here to here it is called de-superheation, you are bringing back. From here to here, what do you call going in this direction? Huh? Condensation, it is a condensation. Okay. And this is cooling part, sensible cooling. Okay. So, then what happens is if you expand like this, it is better to take saturation condition, not the superheat heat condition. What happens? You have to bring it down and then use it like that. Instead, wherever it meets this curve, there you bleed it, but you can still do it from there higher side, but if you go for a single reheat, single feed water heater, you have to go for this. So, now you can plot that, no? I hope you have plotted, otherwise you want me to give, I will give you this. Check it whether you are getting the same or different. 1 to 2 is expansion, and at 2 it is taken. Again this is part is de-superheating, because I have mentioned here why, because at different pressures, suppose if you take it here, then it is a saturation. You can take like this and also mix in the condenser, or you can take here and bring it here and mix here. You can mix anywhere. So, you are bringing it back to the condenser here. See, after this part is taken here to till the saturation, and then it is mixed in the condenser at 0.8. So, heat addition, I hope you understood this, or if you have not understood, I will explain again. So, now what is it is a closed feed water heater. Feed water heater is a heat exchanger, okay, and heat transfers from high temperature fluid to the low temperature fluid, okay. Which is high temperature fluid? The steam which is taken from here to here, this is the high temperature fluid, and it is losing heat. So, where is a 0.2? 0.2 is here, and where it is going? 0.7. So, this is the 0.7. So, from here to here it is losing heat, and which one is gaining heat? This one, where 5 to 6. So, from here to here it is gaining. Now, you have to add heat in boiler. So, here where is the boiler heat addition? From here to here, here to here. So, your steam flue gas flow is in this direction. So, if there is no regeneration, the temperature difference is this, but whereas now it is from here to here. So, therefore, this irreversibility is reduced and made close to the flow. That is why regeneration in this case is used. So, from the heat is transferred from here to here at this pressure, but after heat transfer we are mixing into the condenser, but that operates at low pressure, and again it is a uncontrolled expansion. That is why it is represented dotted lines. You have seen in throttling, it is a throttling. Here enthalpy is same. Okay. In a refrigeration cycle you must have seen this symbol. Okay. So, this is added here, and why 8? Because here this is made such a way that it becomes liquid. So, here it should be liquid. This trap ensures that it comes as a liquid. Okay. Now, you can find out the efficiency of this. Okay. What is efficiency? Work done by heat input. What is the work done? 1 into H1 minus H2, 1 minus m into the H2 minus H3 by of course, the pump work minus pump work by heat addition. This is H7 H1 minus H6, that is a heat addition. Okay. So, now you can do that. This I have already mentioned, this is called heated drip or trap. The trap passes only liquid, no vapor, it does not allow any vapor to this one. If it allows vapor, okay, assume that it allows vapor, okay, there is no trap, what will happen? How this curve would have been? It will come somewhere like this. So, this is a mixture. Okay. This is a mixture both liquid and vapor. When you take it to this point, what is the meaning of that? There is only liquid. This is a liquid line, no? You are going to taking to the liquid line and then from there you are mixing it up. So, then you will lose so much. State 7 is full liquid, but there actually at state you do not mix up with physical and the picture, okay, physical and the TS diagram. That the meaning of that is after 7 there is a trap, okay, that allows only liquid. That means at the 7 itself is you have a trap, okay. So, at 7 it completely converts into liquid and this is a liquid line, is not it? This is a saturation liquid and this is at 7 is liquid, not 8. 8 is a mixing point. So, you got my point. 8, because after meeting 8 what happens is in the condenser the further heat rejection happens from here to here. So, the stream which is coming at 8 will have certain amount of heat that has to be rejected. You got my point, into the atmosphere by here in this. You got my? Okay. Now, going to regeneration with more closed feed water heater. See here you have seen what is this? Drains cascaded backward. See, drain means after heat rejection this becomes drain, okay. This drain cascaded back, it means going back to the condenser. You can take this and put it here also, no? Why you are taking back and putting in the condenser? This after this you can put it here also. What is the difference? How do you put it? Can you put that back front side? This is forward, this is backward. Is it possible or not? It cannot go on its own because this pressure is different from this pressure, okay. Then how do you do? Again you have to use pump. If you use pump here, it does not work. Why? Because you cannot pump two phase mixture. This becomes again you have to allow till the end, then again you have to put a reservoir here and then pump it. Instead of using single two reservoirs, you are pumping it back, you are cascading it back. This here if you cascade there is no pump required, no because it is a high pressure to low pressure. So, now if you look at that instead of taking one feed water heater, if you go for more bleed steams here and then you use one feed water here and then take it to this and then feed it to the condenser here back and there is only one pump, okay. Can you plot it on TS diagram? See, once you know because in order to identify where exactly these points are, you need to go for schematic and a TS diagram. These two are important. The rest of the things are easy because you are just looking at the enthalpies and doing it. Just finding enthalpies from the steam tables and finding out performance. So, the schematic of that is this. TS diagram of this is this. So, when because here 1 2 after from 1 after expanding to 2 some blood stream is or some bleeding is done, then that further expanded here and some more is taken and then further expanded to the condenser. So, here most important thing is this is a boiler pressure, this is feed water heater 1 pressure FWH, this is a feed water heater 2 and this is another pressure, okay. This pressure is different from this pressure. So, it is taken at a higher pressure and then it loses heat to the incoming stream and then goes back and put it into the this is taken here and put it into this, and then both of them go to till here and then mix into this, the stream is coming from here and another one and becomes one and then goes into these two are becoming one here and then goes into the condenser here, and after that then further heat rejection and is the same as the previous one. So, you can have as many number of so essentially what is happening is this is see from 2 to 11 the hot stream and the cold stream is from here to here 7 to 8. Okay. So, you have seen the point 8 here, the point 8, then your heat addition will be between these two. So, otherwise it should have been like this. So, we are reducing this, no, we are eliminating this and making the input, the water which is entering into the boiler will be close to the close temperature difference to the flue gas or the heat addition. That is what reversibility reduction. So, if you go more number of feed water heaters, it will be more closure. So, overall mean temperature Tm, mean temperature of heat addition will be higher. So, when the feed water operates, all these are closed feed water heaters, they are not open, the streams are not in contact, only where are they coming in contact? Here, condenser, because all of them are coming and mixing, no, as the condenser is a mixing point. See, if the feed water heater taken, if the stream bleeding is taken at or blood stream is taken at higher pressure, it is called higher HP feed water heater, high pressure feed water, and LP feed water, low pressure feed water. So, you can go for any number like this intermediate also. See, we have marked here on this line, this constant pressure 7 and 8, okay, 7 and 8. If you write energy balance for this feed water heater, what is the energy balance? How do you write energy balance? M2 into H2 minus, this is what 11, H11. This is the heat which is lost by the stream here, and heat gained by the, which is equivalent to H minus H7, correct, and 1 kg of mass. Okay. In this, if you look at this is a balance. Now, we need to find out what is H7, okay, or H8. This H7 comes from the balancing this one, another one. Okay. How do you balance that one? See, M2 into H, this is H11. Just I have to use my specs here. So, H12 minus H9 plus M3 into H3 minus H9. this one, no? This is 9 and this is the temperature difference, this is the temperature difference. That is, this is the one here and the gauge which is equivalent to 1 into H6 sorry H7 minus H6, correct? H is the same, both are same, but here you will have a trap, that is all, it goes into the liquid, enthalpy is same. So, this is what here. Then most important thing is, what are these? These are heat exchangers, isn't it? These two, I hope you I will erase this, because you should understand. I am trying to convey one important point, which is that terminal temperature difference. Okay, sorry. See, if you look at these, you have studied in heat exchanger, temperature versus length or height, length. This is in a counterflow heat exchanger, you know this. So, this point, see here, if you look at this is a out, this is a in for this heat exchanger, this is in and this out. This 0.8, you see that 0.8 here is, this is the one it is losing heat and this is the gaining here. 0.8 is it, where is it? 0.8 is here, 0.11 is here. Okay. This working fluid temperature, out exit temperature is higher than this, correct? Can it be possible? 11 is here, this one, sorry, and 8 is here. Is it possible? Possible. What is the meaning of that? See whether this temperature can be more than this temperature. The temperature of this is a cold fluid, no, which is heated, and this temperature E can be more than this exit temperature. It is possible, but this cannot be more than this inlet temperature. You got me? This exit temperature cannot be more than, see this temperature T8 cannot be more than T2, because we are taking fluid there, but it can be more than exit temperature, correct. So, therefore, here we are defining a temp which we call TTD, terminal temperature difference, which is equivalent to, this is 11 is on the saturation line, okay, and here saturation line, T saturation at that minus the T out is called that terminal temperature difference. So, you got my, see terminal temperature is defined as here for a closed feed water heater as saturation temperature of the bled stream to the exit water temperature. What is saturation temperature? T8 here, exit temperature is saturation temperature is T11, exit temperature is T8. So, T8 minus T is 11, T11 minus T8. If you look at this one, what happens to this? It is negative, correct. And you look at this here, this can be also lower than that. If you look at this is a hot fluid and this is a cold fluid, okay. If the cold fluid outlet temperature can be lower than this also, it can be higher than the exit or can be lower also, okay, it is possible. So, if it is this is a T9, if for this it is a T9 is saturation temperature and exit temperature from this is T7, okay, you have seen here, no, this is a T7 here, T7 and T6 from here to here, rare. So, this temperature is lower than this. So, here the saturation temperature is T9 minus T7, this is also TTD. Here this is positive value. So, TTD can be, terminal temperature difference can be negative or positive. So, therefore, this drip is used here saturation. How do you find out saturation temperature? You look at the steam table corresponding saturation line, you can find out the temperature. So, to avoid water, I think I already used a drip pump into the feed water stream, this I have already explained. So, all the heat is brought it here and thrown here. So, this heat plus this heat is in the condenser, but the overall size is relatively smaller than the if it would have been without feed water region feed water heaters. The next type is, I will complete, we have another 6 minutes. So, the next one is closed type feed water heater, drain pumped forward. In the previous case we brought it to the condenser, and the problem is, as far as the mass of the mass holding capacity of the condenser is remains same 1 in case of pumping back, but only thing is the heat rejection may be less if you go for feed water heater. So, if you look at that previous one, the previous case, this has to handle the same amount of mass, this pump, okay, but heat rejection is different if this would have not been there. Heat rejection will be this H4 minus H5 into 1 minus M1, heat rejection in this, what is the heat rejection here in the condenser is, this is the coming here, this 1 minus M1, if you take this this here is M1 M2 is given, no. So, suppose if you take this is M1 and this is M2, this is 1 minus M1 minus M2, the mass is going here, M1 minus M2 is the 1, this into H4 minus H5 is from here. Apart from that, this M10 is coming here, these two are coming here into this, that is plus M1 plus M2 into H10 minus H5. This is the heat rejection in this, clear. So, if this would have not been there exactly 1 into H4 minus H5, then now this heat rejection is less here in this, but the if you look at the mass of this, because it has to hold entire mass there. So, mass remains same 1 minus M plus this, if you add these two it will become 1 again, mass is same, if you write mass balance is same, but energy balance is different. So, therefore, then the bulky, condenser will be bulky. Why do not we go for this way, we keep the condenser smaller size, okay. So, then what you do is you bring the streams to the forward rather than going for backward. So, this is called drains pumped backward, sorry forward, pumped forward. Then here you see that it is taken at high pressure, then after drain it is pumped to the main same stream here, because this pressure is different from this pressure. So, therefore, you need to have a pump, and same way another pump here. So, how do you represent in TS diagram? It is like this, there is nothing is going to the condenser, everything is pumped forward and put in the mainstream. So, here you can write 1, 2, 3, 4, then 5, 6, then you have other drains here 2 to 11 is 1, and this 11 to 12 is a pumping process here, 2 to 11 is here, and it is a heat reject, and 11 to 12 is pumping here, and then another stream is taken at 3 to 13, 3 to 13 is 3 to 13 here, this is 3 and this, and then pumped from 13 to 14 here, this 13 to 14. This is for pumping pressure point of view, this is the pressures, okay. because, and again there is a condenser pump which is from condenser pressure to the boiler pressure, a single pump, but the mass is different here, mass handled by this is different, but pressure, that means you have different pumps with different flow rates with the different pressure ratios. Okay. This 5 to 6 is condenser pressure to boiler pressure, and this 13 to 14 is feed water heater pressure to the boiler pressure, and then this one is feed water 2 to boiler pressure. These are, so therefore, if you look at this stream versus this stream, okay, if you look at by a representation point of view, how they look like, it looks like a co-flow type, no. Co-flow means this is, if you put this and it is coming like this and also it is going like this, but it is a it can be a counter flow heat exchanger, but I am, if in this schematic flow diagrams is forward flow. Okay. So, and you can represent these points on this here. You can also find out TTD, terminal temperature difference, terminal temperature differences for so that you can find out the feed water heaters. Okay. So, this are mentioned, and now I have already explained. So, this is it add several pumps are there. In the previous case, if you look at only one pump is there, but here 1, 2, 3 more pumps are there, more pumps, more complexity. See how many feed water heaters you can add like this. I just now I mentioned in the couple of minutes back that they can be 7 to 9, but what happens is in that at least one should be, see when you have a open feed water heaters you have more irreversibility, but at least one should be open feed water heater in order to avoid lot of pumps. Many pumps are there. If you go for 9 means 9 pumps are there, 9 pumps means 9 your pumping power will be higher. So, therefore, what you do is instead of you have to have a trade off, bring all the streams and put it somewhere and then pump with or 2, 3 pumps. So, out of 7 or 9 there should be one open feed water heater, and not only it is required for mixing, but also you know that the steam is what is the meaning of steam here? Our working fluid is what? Working fluid is water. So, water can be in different phases, liquid phase as well as vapor phase, and when it is going through the pipelines, pipelines are made of what? Boiler pipes, mainly steel, okay, high carbon steel pipes, and when it is passing through the pipes with a higher different pressure, it interacts with the pipe material also. Then there will be production of non-condensable gases. So, those non-condensable gases need to be removed on a regular interval, otherwise there is a possibility of blockage, and not only blockage, but also heat transfer problem, because if you take a pipe here and in this pipe you are adding heat and the fluid is going and you have some bubbles here, some vapor bubbles, then heat transfer to the bubble is different, heat transfer coefficient here it is different from the liquid. So, therefore, because of uneven heating of the fluid which may result breakdown of boiler tubes. So, therefore, the gases should not be there in the pipeline. So, therefore, it has to be removed, and that can be done by this. It looks like this. Okay. I have already explained, no need to. So, therefore, there is one open feed water heater in the system which we call deaerator, because removing the non-condensable gases continuously is called deaeration. Deaeration means remove the gases. Okay. So, if you look at that, you can see that there is one condenser, then one open feed water heater, all closed feed water heaters here. So, these two feed water heaters are brought back here, and this feed water heater is pumped forward. Okay. Here you see that this is going back to the condenser, but whereas these two are going to the open feed water heater, you can see this. and if you this is again I have already mentioned, either these feed water heaters are horizontal or vertical. This one either like this, fluid goes like this, another fluid comes here, or like this, one goes in this direction, the other one is going in this direction. So, essentially there can be more than 7 to 9 feed water heaters depending upon the capacity. Then we have to discuss regeneration, but we discussed reheating separately, but we will combine in the next class. I will stop here. How to make combination of both regeneration and feed water heater, reheat. Okay. So, in the next I will stop here, and if you have any questions let me know. Thank you. I will close this.